So hello, guys. Thank you for joining. Thank you for coming to my talk. I'm Alessandro Pomponio. It's my first time at KubeCon today, so I'm very excited, especially to be on the first Kyverno. I'm a research software engineer at IBM. I work in mostly orchestrating and executing computational experiments at scale. But as you might be happy to hear, this is not what I'll be talking about today. I'll be talking about how, basically my side gig, right? Which is administering 2 bare metal OpenShift clusters at IBM Research, and how we went from a chaotic, manual setup, inefficient, to one where we don't have headaches anymore, thanks to Argo CD, Kyverno, and Kueue. Before I start, though, I need to give you a bit of introduction to the field I work in, which is called accelerated discovery, right? AD looks at the intersection between AI, hybrid cloud, and quantum computing, and its goal is to, and I quote an IBM PR person, drastically increase how quickly we can discover solutions to tackle today's most urgent problems, which I think is pretty cool. And in this context, we collaborate with researchers coming from any kind of background, basically, AI, HPC, chemistry, mathematics, more, and more, right? And in addition to working myself in these topics, my team manages 2 bare metal OpenShift clusters, as I mentioned, and for our colleagues to run their workloads on, which is where everything started for this talk. So research computing has its own challenges, but I will focus on just 3 today. The first one being that researchers often aren't Kubernetes experts, right? They're used to oftentimes having an HPC background where they have whole nodes at their disposal, and the way they emulate the same behavior on OpenShift or on Kubernetes is by creating pods with sleep infinity and accessing them via remote shell. And unfortunately, this also means that they often leave them running long after their training workloads end, which means GPU go to waste. Another problem is that workloads are often bursty, and there's a lot of resource contention, right? Because oftentimes there may be little to no workloads coming in the cluster, but when it comes to deadlines for conferences like NeurIPS, AAAI, you bet that the cluster is working at full capacity. And what we've seen, especially with other colleagues that run like batch workloads for document extraction, text extraction, is that large CPU jobs can cause scheduling issues by basically using up all the CPU and memory resources on GPU-enabled nodes, causing us other headaches. And lastly, there's what I already introduced as being the side gig problem. And I'm a researcher. I'm not a professional platform engineer. So especially when we started managing these clusters, we didn't know how to best set them up. And we had a lot of manual steps. And combined with a lot of non-expert users, this caused us to be swamped with requests for even simple changes, which we then had to manually deploy on 2 clusters. And it just slowed down our research. So at some point, we decided we had enough. We had to make some changes. So I put 4 on this slide. The first one being shifting namespace management decisions to the users and removing manual deployments. This will remove the bulk of our workload and for trivial tasks and free a lot of time for us. We also wanted to introduce policies that prevent these large CPU-only jobs from swarming GPU nodes and block interactive GPU pods, making sure that GPUs don't go to waste once again. We also wanted to introduce a queuing system to give some fair access to GPU resources. And we did this by calling in the sheriffs. We have Argo CD, Kyverno, and Kueue. OK, so let's start with the changes that we did towards automation, right? We basically go through our goals again. So we don't want to be the ones implementing changes for our users' trivial tasks. And we do this by shifting namespace-level decisions to them. Users submit change requests, and admins review them, ask for changes when needed, and approve them. We also want to avoid inconsistencies and eliminate manual deployments. This We do this by adopting GitOps approach, in our case by using Argo CD, but more on that later. And we want to create configurations that are easy for both our users and for ourselves, admins, to maintain, develop, and extend. For this task, we chose Customize, because we can basically boil it down to plain Kubernetes YAML, for which a lot of documentation is readily available. And lastly, which is like one of the core of this talk, we want to make things as automated as possible, and we also want to do less things as possible. We want to be able to change our policies, whether it's default permissions or anything else for that matter, and we want these changes to cascade down to all the namespaces that our users created. Not only that, but we want the namespace, the full life cycle of the namespace to be automated, whether it's from its creation to its deletion. So at a glance, this is what we want to have. At the foundation, as admin put the plumbing in, right? We set up Argo CD and our Git repository, and immediately start creating the building blocks. So at the core, we have a shared base project definition, which is full of sensible defaults, hopefully, which depend very much on your environment. So our defaults might not work for you, but we have like group membership roles, role bindings, quotas, and more. And this is basically what gives us cascading changes, settling in at this low level. Then, immediately above it, we create a collection of common add-ons that users might want access to, like seeing GPUs on the cluster viewer role, and more. Then we step into the user land, where our fellow researchers create their own projects. We want this to be very simple. And in our setup, basically, it boils down to creating a folder in a repository and adding a customization and a group file, copying it basically from one of the examples. In the background, since we're using Argo, this will have to create Argo applications, but we don't want people to create them manually, so we have something for it in just a couple of slides. So automating, right? To minimize maintenance, you have to start from choosing your tool. We chose, since we use OpenShift, we chose OpenShift GitOps because it really reduces operational complexity. You just press a button, and it installs and configures Argo CD in a way that we like. It's fine. But you can also obviously use Helm charts. You can also use other tools. You can use Flux or whatever you need. You might have to make some changes. Again, here, we chose Customize because it's easy for everybody involved. And it really plays well with this idea of a Lego-style approach, where we create a base and we add some more like small blocks on top of it. And to make it even easier, you want to really minimize the changes that these non-expert users need to do. And in my opinion, this goes back to the idea of add-ons, but also by creating fully fledged examples that users can just copy-paste and change a couple of lines in and reset and be done. Because they really don't want to do work, just like we don't want to do additional work that we don't need to do, right? Then I review their PRs and ask them to remove excessive permissions if there are, and then I approve it. So this slide is just to show you that we keep it simple, stupid, right? We just have an empty group definition. People will just add a list of users they need to give access to. We have limit ranges because we have resource quota being provisioned as part of the defaults-based deployment. So we need to avoid complaints. We need to add some default to resource requirements and limits for pods that are created through operators that maybe don't set these values. And this is just a small customized file. OK, so I said we used Argo CD, and Argo CD uses applications. So applications are groups of Kubernetes resources defined by a manifest. And they're not super easy to create, and they can be very time-consuming. So I definitely don't want them to have to create them, and I definitely don't want I to have to create them, right? So we created this application set to create them automatically. So basically, in Argo, you can define generators. So we tell Argo, clone this repository via SSH and look at this user's project directory. And inside it, you will see folders. And these folders need to become their own Argo application. So here, we use the path details to template an Argo application. And we ask Argo to create the namespace if it doesn't exist. And we do two very important things, which you see at the bottom, hopefully, because it's small. But we prevent drift by adding self-healing, so that if a user performs a change manually, Argo will amend it and will bring the state back to what's defined in the Git repository. And we add pruning, so that if we remove something from the base project, it gets pruned in the cluster as well. And this is just to show, my small project that I created for people to copy from. And we have like 30 or something projects that people have created. It's not a lot, but people have accepted this way of doing things, and it's really worked well for us. So to recap, basically, users now propose changes by submitting PRs to their Git repository, and thanks to a simple customized setup, and admins only need to review the PRs, and changes are deployed instantly. We guarantee with this compliance, traceability, and more, thanks to the use of a Git repository and a GitOps setup. With the use of self-healing, we also prevent manual changes from persisting. And also, by automating everything and giving the users a bit more power, we have basically zeroed support requests on Slack. So going back to this slide, we've done the first step, and now we need to move to tackling the issue of large CPU jobs and interactive pods. So our goals for our policies is to first fix what I just mentioned, right? We want to make sure that we fix these large CPU jobs and interactive pods by performing transparent changes when we modify user resources, but also at the same time, we want to be very explicit when we block something, letting the user know why this happened. We also want to avoid doing more harm than good with our policies, because our policies should not disrupt a researcher's workload more than what they were doing before by doing their, let's say, uncompliant or non-compliant things. So we need to build in exception mechanisms and some level of observability to see when we make mistakes. And lastly, which is the refrain of the whole presentation, we want to do things quick, and we don't want to learn new languages like Rego, and we want to do a lot of copy-pasting, and which is obviously where Kyverno shines. So problem number one, large CPU-only jobs. So you might know that the simplest way to avoid scheduling CPU pods on GPU nodes is to add either anti-affinity or affinity rules, right? And we had originally, well, you showed it in the previous talks as well. We first started by asking users to apply them manually, but users forget, of course. And with Kyverno, we can do this by inspecting the contents of the resources that are being created. So when we receive a job, we check if they're requesting, in this case, but we should check the limits as well, GPUs. And if the job does not require any GPU, we just add this affinity rule saying, do not schedule on nodes where the nvidia.com/gpu.product label exists. You could do this with gpu.present, but our clusters are a bit weird because we have network-connected GPUs, whatever, and we had some problems with the NVIDIA operator, so we did this. Now, the second problem, interactive pods. So from what we've seen, people were either running pods with sleep infinity or tailing dev null, but they could always come up with something, right? We create a block list of these commands, and they will find another one that just escapes it, right? So we went through the Kyverno documentation and found this amazing policy, which just blocks execing into pods by namespace labels. And this makes a lot of sense. We can just prevent people to use these kind of pods interactively, which will basically render them useless. So we chose this approach. We created our own policy, which it's largely the same. We just added a few things, like we allow cluster admins to perform these execs because we don't want to block ourselves from accessing these pods and seeing what people are running. And also, we have a config map which just has a list of namespaces we want to exempt this policy from. But what's important, of course, is also to have a message which is very clear, saying, executing a command in this container is forbidden. Just ask us if you want an exemption to this rule, and we will have a look at it, right? Now, what we might ask ourselves is, what if it's a bit too harsh? It's a bit too much, It could very well be. So we need to test things out, and you could do like audit policies. We went a bit harsh. Okay, we just applied the policy to a small set of namespaces with our power users, which do the non-trivial things. And we had a look with this other policy that I found on the documentation. We created events on every exec that people were doing, but just with a small modification, I can now see whenever somebody performs an exec, I can see, OK, these are the groups, this user is part of, this is the person that did it, and these are the commands that they ran, right? And this is very important because it allowed us to see that we were doing too much. So we were blocking people from running OCCP and OCRsync to copy files in and out of pods. And we were also blocking execs on non-GPU pods, which could be fine. But since we have plenty of CPUs to give away and not many GPUs, we're fine with letting people do whatever on CPU-only pods. So let's zoom in a bit on the changes that we did to these policies. So at the top, we ask Kyverno not only to load our namespace exemptions from the config map, which you can see here, but also we ask it to perform a call to the API server and check how many GPUs the pod a person is running this exec in is requesting. Again, you should check the limits as well. And at the bottom, we see that we have now a small allow list of commands like tar and rsync to allow OCCP and OCRsync, as well as we only deny the request if pods are actually asking for GPUs, which you can see there at the bottom. A small bonus is slightly unrelated, but I found this type of policy to be very helpful. Just label resources that are being created with an annotation of the person that did it. It really helped us from, instead of rummaging through logs and whatever, we could just see the annotation and see, oh, OK, this PVC was created by this person using an old storage class that we want to deprecate. We will just reach out to them whether they want to move it to the new storage class or they just can have it reclaimed. So we use the policy that we've seen to fix the issue with large CPU jobs and interactive GPU pods. And also, one of the best results, in my opinion, is that users are largely unaware of the policies. So some are by definition, because we are transparently making changes, but people don't complain. And also, by having these policies, we were able to figure out that some workloads could be moved to more towards jobs and be more cloud native, while others, we had to learn that really required this kind of interactivity when using GPU, because we have some of our colleagues working on geospatial models, and the images that are generated as part of the training really have to guide the way training is being done, so they need to have an exemption for it. So we're on the final stretch. We have 3 check marks, and we just need to make sure can access GPU in a fair way. So in our experience, most of the research workloads are not time sensitive. And despite that, people seem to act like they are. They create 1 million jobs, they create 1 million pods in a way that overwhelms the clusters. So we want to have an HPC-like queuing system where we also make sure that people can access specific GPUs because they might have constraint on CUDA capabilities, or simply their LLM does not fit into 40 gigabytes of memory anymore. And so we need to make sure they can still choose a specific GPU, but also we want to have a small queue, or like a queue for people that just need a generic GPU because maybe they're testing one of the small geospatial models that they're working on, right? So our clusters, I mentioned that we have network connected GPUs, but we also have just a ton of weird, like old GPUs, because we have acquired over the years, and it's a waste to throw them away, right? So some of these can be helpful, again, for testing these small models, but that's also about it, you know. With Kueue, we can define subset of nodes based on resources that they provide using resource flavors, which you can see at the top there. In here, we have labeled set a resource flavor for nodes that have the label that's been added by the NVIDIA GPU operator, in this case for H100 nodes. And we use this kind of resource flavor to create an H100 queue. So if you need an H100, for example, because of its CUDA capabilities, we define a subset of the resources that you can have available when you submit to this queue. And this really helps us solve the first problem, right? We want users to be able to choose what kind of GPU they require, and they can access it via the queue. But at the same time, we use this kind of marker called GPU cohort, for example, because Kueue has a mechanism where queues can borrow resources from other queues. And this really helps us deliver the second point that we have. So we can create another queue that it's a generic queue that's in the same cohort that has absolutely no resources dedicated to it. And if a user submits to this queue, it will fetch resources from the other queue that we have defined. And this will lead to faster turnaround times because you're not requesting a specific GPU. So now resource access can be fair if we use Kueue. Workloads are just enqueued and they eventually execute. And also users can both still access specific GPUs or a generic GPU queue. In case you're hungry, like I am, and you have dozed off for the past 25 minutes, I can give you a quick TLDR. So us admins have less headaches. The user support queries have basically been zeroed by adding automation and giving them a little bit more power. Deployments are not manual anymore, and using GitOps guarantees us visibility, auditability, traceability, what more have you, and self-healing guarantees that everything stays the way we have defined. So on our end, policies automatically solve misconfigurations and resolve these problematic behaviors. And that also makes users happier, because policies have greatly reduced the resource contention on the cluster. With all the changes that we've made, namespace level changes are much quicker, because a user does not have to ask me to implement a small change. And maybe I'm busy, and I can only do it in an hour. With this, they just propose the changes, and within a second, it's deployed. And GPUs are also accessed more fairly. The key takeaway, though, be empathetic. Make sure to think like your user and understand where they're coming from, and make it as easy as you can for them. And this is it. Thank you very much. There's a QR code for links to talks, blog posts, my LinkedIn profile, what more have you. Thank you very much.